Hello, we're going to look at example 11. It says to first solve the equation z to the fifth equal to 1 in complex numbers. And this is the symbol for our complex numbers. And then B, we're going to let, this is the Greek symbol omega, omega not equal to 1, be a solution of a complex number z to the fifth equals 1. Or just the equation z to the fifth equals 1, right? And then show that 1 plus omega squared plus omega cubed plus omega to the fourth equals 0. So first we'll start with A. So A, it wants us to solve the equation z to the fifth equals 1 in complex numbers. Well, I know that if I find z of k, well, this guy right here is just going to be CI at, a little messy here, guys, sorry. Let's just do this. We know that if it's z to the fifth equals 1, and then this is the same as CIS at 0 degrees, that's the equivalent to 1, right? And then we can use De Moivre's theorem. Well, not De Moivre's theorem, but the formula for finding complex numbers. This is going to be 0 plus 2k pi over, since it's the fifth root, it's to the fifth, right? Good. And then this represents all our solutions. I'm not going to write them all out individually, but if I wanted to, I can have to do k equal to 0, 1, 2, 3, and 4, right? These will represent our 5 roots. So you can do that. So these are, this is I've solved it, right? They never asked us to do it out in anything in particular, so I'll leave it at that. Now next, B, we want to show that, well, omega not equal to 1 be a solution. So omega is a solution, but just not the one that says where it's 1. Be a solution. Show that when we sum up 1 w omega squared plus omega cubed and omega 4, we get 0. So if you notice that this guy right here is a geometric sequence, right? It's a geometric sequence. It's got a first term of 1 and a common ratio of omega, right? So I can sum up these terms, right? I know that the sum of those terms are going to be, I could say, a sum of 5 terms, right, is going to be, well, my first, if you remember the formula for a geometric series, for a finite geometric series, my first term is 1, then it'd be 1 minus our common ratio, which is omega, omega to the fifth, right? And all over 1 minus omega, right? But we also know from the original problem that z to the fifth equals 1. Well, omega is one of our roots, right? It is a solution, so omega to the fifth, it has to be equal to 1. That's when the easiest solution we know that we have for it, when omega is equal to 1. Or omega to the fifth equals 1, right? So, and so I can just, from this formula, I get 1 minus omega to the fifth is equal to 1 over 1 minus omega, and so this is equal to 0. And what do we get here? Well, now this sums up, this expression here is this sum right up here. So now I know, therefore, that 1 plus omega squared plus omega cubed plus omega to the fourth, that sum, we showed that is equal to 0. Now, the important part to think about this, right, is would this change for higher powers of 5? What if I went to 6, 7, 8, 9, 10 for this expression right here, right? And it will not. You can keep doing this over and over again. It's not a proof, but this will always happen when we're talking about equations right here. And this is what we're going to go over in a bit. Some of the properties of this is what we call roots of unity. Roots of unity. Right? It's always going to happen out like this when it's equal to 1, some complex number like this. We're going to end up with our radius is always 1, so it's going around in a circle, and it's a radius of the unit circle. And we'll see more properties of it. But this will always happen. The sum of this sum like this of our possible roots that are not equal to 1 of the complex numbers of the roots of unity, when we sum them up like this, they're always equal to 0, right? So what we're going to do next is talk a little bit about the roots of unity and see what happens, right? So if I were to solve this expression right here for the nth power, right, I'd have z of k is equal to CIS of 2k pi, 2k, 2 pi k, right? All over whatever my nth is, right? And then we can talk about, we're going to look at particular cases of n, right? Well, if we did n equals 1 and then k equals 0, it would just be 1, right? And so it's just a real number 1 right here, right? We'll take this to be a distance of 1 right here. So we'll say that this is the unit circle right here with 1, right? And we'll do that with other. And if we did n equals 2, well, that would be n equals 2. We'd end up here and here. So we still got purely real numbers, no complex. It's not a number that's other than a real number. So we're going to start and look at the first one where n equals 3, right? So with n equals 3, I get z to the 0, and then I'm going to have 2 pi over, well, it's just going to be CIS of 0, right? The first one when k equals 0, and then k equals 1, and then I'm going to have CIS, and then it's going to be 2 pi over 3, right? And then I can get z equals 2, and this will be my 3 roots for n equals 3, and it's going to be 4 pi over 3. So CIS 4 pi over 3, right? So what are my roots? Well, the first one is just the real number 1, right? So I get, let's use this number. This is the unit circle 1. We'll go right here. And then the next one's at 2 pi over 3. That's going to be right there. And then so I get z of 0, z of 1, and then the other one's going to be down here at 4 pi over 3. So 2, 3, 4 pi over 3. This is z of 2, right? Those are my 3 roots for this when n equals 3. Now, what about when n equals 4? N equals 4. Well, the first one, we're going to get the same thing, 0. It's going to be CIS of 0, and this is going to be equal to 1. And then at z of 1, I'm going to get CIS of pi over 2. It's going to end up being, when you calculate it, pi over 2, right? Then z of 2, which is CIS of pi, this time when this equals 2, and this is 4, it's just going to cancel out and be pi, and then z of 3, we're going to get CIS of, that's going to be just 2 pi, 3 pi over 2, my bad, 3 pi over 2, right? And so we get the complex numbers in this plane. First one, we get 1 again, right? We get 1. The next one's at pi over 2. Then pi, and then 3 pi over 2 right here. So we got z of 0, z of 1, z of 2, and then z of 3. So we've seen 2, 3, and then we're going to do, I've seen 3 and 4. We're going to do one more. We're going to do one more. We're going to do, we could do 5, but it's not a little bit harder to grasp. So what we're going to do is going to do n equals 6, right? That'll be an easier one to do. So let's get this out of here. We're not going to do this guy right here. Was going to do another one. Let's do n equals 6. So when I do n equals 6, I'm going to have z of 0, which is CIS. It's going to be CIS of 0 again, right? Sorry, that's S. And then z of 1 is going to be CIS of 2 pi over 6, which reduces to pi over 3. And then z of 2, which is CIS of 4 pi over 6, which is going to reduce to 2 pi over 3. And then z of 3 is going to be CIS of pi, right? So 3 times 2 is 6 over 6 is just pi. And then z of 4, right? That's our 5th out of our 6 roots. CIS is going to be 8 pi over 6, which reduces to 4 pi over 3. And then the last one, z to the 5th, is going to be CIS of, well, it's going to be 10 pi over 6, reduces to 5 pi over 3. 5 pi over 3. Good. And then when I plot these, I get this one z of 0. Next one's at pi over 3 right here. That's z of 1. The other one would be symmetrical right here, z over 2, and then we get pi z over 3, and then this one right down here, z of 4, and then the last one right here is 5 pi over 3, which is z of 5, right? And there you go. Now, let's see, what have you noticed? If you've noticed anything, what's going on here is first thing you should notice is look what every roots of unity share in common. They all have the same root, and that's just 1, right, for each of them. And that will always turn out to be true. But another thing you notice is that they're always evenly distributed from the same angle, right? Here and here, right? And this one was 2 pi over 3, right? For this one right here, it ended up being pi over 4, right? And then the last one we did right down here ended up being at increments of pi over 3, right? All of them are represented by pi over 3. Or better yet, all of them are going to be separated by 2 pi over n, and that's what's going to end up happening. So they always share the root 1 for the roots of unity. They're always evenly distributed by 2 pi over n, and we've shown about their sums in the previous problem, example 11. So I have them all all the properties kind of outlined here. And so if you have a roots of unities for some z to the nth equals to 1, they lie on the unit circle. That's the first thing, right? They lie in the unit circle for r equals 1. Z of 1 is always a root for n is equal to, n is in the element of the positive integers, right? They are equally distributed or separated by 2 pi over n. And we've shown in the example 11 at the beginning of this video that when we sum up some root where some omega is a root of z sub n, where actually we got to say that omega is not equal to 1, right? It's not that root, and it's 1 plus omega squared plus omega all the way up to n minus 1. It's always equal to 0. So here are our main properties, and I hope that all made sense. Thanks, guys.